Hello everyone, welcome to this next lecture in the DC to DC video series. It has been a bit of a break before I started this video series since I was away from my city. So now to continue with it, in this lecture I'm going to lay the foundation of the need for isolation in DC to DC converter series. So this is before I get started with the next set of isolated DC to DC converters, which are the flyback, the forward and things like that. So I just wanted to talk about what is the need for isolation. So as before I start the lecture, a little bit of brief background that if you are interested in these kind of video lectures but you would like something a little more comprehensive, I do have an entire online course on simulating power electronic circuits on the MOOC website Udemy. And this is my very first course, which is simulating power electronic circuits using Python. And in this I talk about the entire process of simulation, which includes installing the software, some basic power electronics, and also a case study of simulating a buck converter. If however you are interested more on the control side or the digital signal processing side, I have another course on the basics of digital signal processing for power engineers. In this I talk about how you can use Python and Python packages like SciPy and NumPy to design filters and analyze their performance. And here I use this to design low pass and notch filters as examples. And the last is, if you are interested more on the magnetic side, then I have another course on simulation of magnetics for power electronics using Python. In this I talk about how you can use Python and Python power electronics to simulate inductors and transformers. And in this course, or rather in the next part of the DC-DC video series, I'll be using some part of this course where in this course I simulated transformers. So I will be using this simulation of transformers in the next part of my DC-DC video series. So coming back to the lecture. So as I said, in this lecture I'm going to talk about why we need isolation. So for that I'm going to talk about, let's go over to the circuit of a buck boost converter. So this is the case of a boost converter which we did several months back. And the boost converter is pretty simple. We have a voltage source which has an inductor in series. The switch is connected across the voltage source and we have a diode and a capacitor at the output. Right. So the way it works is very simple. When the switch is turned on, the inductor charges through this voltage source, rather the current increases and therefore the inductor builds up energy. And when this switch is turned on, the output capacitor discharges through the ammeter or discharges to the load. So when the switch is turned off, the voltage source and the energy built up in this inductor are then discharged to the output. So it is the cumulative energy of these two which are fed to the output. That is the reason why the output becomes a boost stage, because it receives the energy from both these sources. Right? And the result is the output voltage is greater than the input voltage. Right? So now the question which I want to talk about is, we have already seen, right? We saw earlier that the output is related. I can just write this. The output is related to the input by the formula 1 divided by 1 minus d. Right? This is the formula. So basically it is the ratio, the turns, or you can, I don't know if you can say a ratio, the step up ratio is 1 divided by 1 minus d. Right? So if we have any ratio, right, which is greater than 0, this will be a step up ratio because the denominator is lesser than the numerator. It's as simple as that. If we keep on increasing this duty ratio, you would expect the output voltage to increase by the same amount. So for example, if we had a duty ratio of 0.9, what that means is you would expect your output voltage to be 10 times your input voltage. Right? It's pretty simple. Just put 0.9 here, you get 0.1. The result is, it is 10 times Vin. Right? Now, this may seem like a really cool idea because now you're stepping up the input voltage, right, by a factor of 10. Now, in this lecture, I'm going to talk about why this is probably not a good idea. Right? that there is usually a limit to how much you can step up using such a boost converter, right? So let me just delete this so it doesn't change my circuit. Let me save it again. Now let's go over to the simulation and see what's happened. Let's go to the simulation library. Let's go to the boost converter and let me just see the results. Yeah, this is pretty much the same. Add the circuit file. This is the same. I don't have to do anything to it. I could just go back to the main page. Edit circuit parameters. Let's go and see what the parameters are. Yeah, let me go. I think what happened, the error here. Okay, let me just show you the error so that you know what happens. You see, the error here means no such file or directory. So it says home circuit simulator document simulations does not exist. This means this usually occurs when you move the simulation files, which is probably what I did, right? I have probably moved the simulation files from one folder to another. So all I have to do is just go to the edit circuit simulations, edit the simulation parameters and put the new directory here. So I just have to go to my directory, go to properties, go to take the parent folder, I think I did a copy again. And let me do a copy this, paste this time. Yeah, so you see it had changed, which is the reason why it was saying file not found. So let me go back again. Because if the directory changes, the working directory needs to be updated because the simulator will look for all files within that directory. So now we have everything. So the ammeters don't really matter. The capacitor is a 500 microfarad capacitor, which is decent. We don't need to change it. The inductor is a 1 millihenry inductor. So this is inductor L1, right? The inductor is a 1 millihenry inductor, which is actually quite big. For a 12 volt system, this is a very large inductor. But anyway, this is just an example, doesn't really matter. We have a 5 ohm resistance, which is fairly large load. And we have a 12 volt input, right? So most importantly, we have a 12 volt input, which is a standard battery, you could say, connected to a 1 millihenry inductor. And this 1 millihenry inductor is what is the limiting inductor when this switch is turned on. When the switch is turned on, the only thing that stops this current from going very large is this inductor. Because remember, the resistor has to be negligible. If the resistor is significant, we have losses in the system. That's not very good. So now that we have achieved this, let's run this simulation. At this and increase, let's go to the gate signal.py. In gate signal.py, let me remove this part which takes in the modulation signal from the other open control modulation signal.py. Let us fix it to 0.9, right? That was what we decided. That is, if we do it at 0.9, we expect a step up ratio of almost 10. So now that we have this, let's run this simulation. So basically we are running the boost converter at a duty ratio of 0.9, which means this switch is turned on for 90% of every switching cycle, right? And therefore we expect the output to be 10 times the input, right? Mathematically. So let's go to the command line, check if there's an error. No, there is no error. The error before was with respect to the file not found, but not anymore. So now that we have this, let's go check out our output voltage. So we apparently got something. This is the output. What is the name of the file? Output voltage plot. So it is this one. So now you see what has happened. It has increased to around 90. It's a little more than 80, right? So it does appear to be boosting it up, right? So you might think that this is working. You are boosting it up. The first thing is we expect a duty ratio, a step-up ratio rather, of 10. So which means we expect this to be around 120 volts. So we are nowhere near that. That is the first part. Now, let's go and have a look at some other variables which will tell you what the problem is. Let's look at the inductor current. And now you see the difference. Now, look at the magnitude of this inductor current. I just hope I'm plotting the correct plot. Let me just see. Inductor current, yes. Now, look at the magnitude of the current, right? It is 175 amperes, right? Now, let's go back once and have a look at the circuit. As I said, when this switch is turned on, right, the voltage source charges this inductor. Well, when you can say charges, it actually builds up the magnetic field in this inductor because the current gradually increases from 0 to whatever value, right? And later, this inductor and this voltage source are then feeding the output capacitor when the switch is turned off. That's how it works, right? But when the switch is turned on, the inductor is the only element which is opposing the increase in current, right? The resistor is negligible. And important to note, we've chosen a 1 millihenry inductor, but even that is a bit too large. For a 12 volt system, you might choose only a 200 to 300 microhenry inductor, which means that we would expect this current to be even larger, right? Now, think about this for a minute. We have a 12 volt battery and we are extracting a current of 175 amperes from it, right? This is totally impractical, right? Because for the simple reason that this current is going to place a huge stress on this switch, because the entire current is going to flow through this switch, right? Now, let's look at something else at the same time. Now, we can measure the voltage and the current across the switch as well. This will tell you about the stresses in the switch. But what is important to understand through this simulation, let me see what else we can plot. The others you don't really need to look at because they would also be similar. For example, if you plot the diode current plot, that would also be at the same level because the same current is also flowing through the diode because the diode has to freewheel. But so it's also the same magnitude. It's just a broken current because the diode current is discontinuous as opposed to the inductor current. But going back to the inductor current, it is quite obvious that if such a large current flows through the switch, this is extremely damaging to the inductor, to the switch. Okay? This places huge amount of stress on the switches. Now, the reason why this huge amount of stress appears is because the switch is shouldering the entire burden of boosting up the voltage, right? The entire boosting up happens because of the action of the switch, right? And this is the reason why the switch takes the entire burden. That's not very safe, nor is it very efficient. Because remember, this switch, when stressed to such an extent, can be quite lossy, which means the efficiency of the system will be very low. Not to mention that this is very risky, and if it continues, you could end up with the switch and the system being damaged, right? So therefore, when you want to boost up the output voltage, you need to take into account that after a certain level, the stresses in the switch will increase to a value which may not be practical, right? And at that level, the switch may get damaged and you may sustain damage in the other parts of the system as well. For example, the diode may also be damaged because the diode is also taking a huge current and also is experiencing a huge reverse recovery voltage. So these are things which you need to take into account. So when you use a boost converter, we cannot just theoretically increase the duty ratio to anything we want, right? Theoretically, this is perfectly okay. 0.9 duty ratio is perfectly okay. Practically, you don't want to exceed around 0.3, right? You don't want to exceed around 0.3. So you do not want to increase. You don't want to, I would say, you don't want to exceed 0.7 maybe, not 0.3, which means you don't want to step up your output voltage by a factor of more than 3. Anything more than this means the switches are under tremendous stress. And if they are under such amount of stress, with time, your devices will get damaged. So there is a practical limit to how much you can increase your duty ratio. So now the question arises, what do we do if we want to step up even more? If we want to step up even more, we must deflect some amount of the stress away from the switch into another element. That element is usually a transformer. So therefore, if you want very large boost ratios, it is advisable to use an isolating transformer to deflect some of the stress away from the switch into a passive element. The reason is passive elements are much more rugged and can withstand much more stress than a power electronic device such as a switch, IGBT or MOSFET turning in them. Right? So this is something which we'll talk about in the next lecture, where we will get started with transformer simulations. But the idea behind this lecture was to lay the foundation for why we need isolating transformers in boost converters. That is, theoretically, after a certain level, we do reach a limit. That is, theoretically, we can increase the duty ratio to anything we want, but practically, there is a limit to the duty ratio beyond which your system is at risk. So you do not want to increase your duty ratio to any limit you want, right? So therefore, with this lecture, I'm going to stop this lecture. And as I said, in the next lecture, we will start simulating a transformer. So as before, if you have any doubts, please do post in the Q&A forum, or rather, please do post in the comments, or email me, or message me on social media, whichever is your preference, and I'll be happy to help you. And in the meantime, if you want to get started with simulation of transformers, feel free to check out this course, which deals completely with the simulation of inductors and transformers. So, with this, I will end this lecture. Thank you so much for watching, and goodbye for now.